Okay, hi everyone. Thanks for joining us today. So today I'm happy to welcome Justin, and sorry, I don't know how to pronounce your
That's
name,
okay. Gottschlich.
Gottschlich, who's a principal scientist and director and founder of the Machine Programming Research Group at Intel. And he's also actually an adjunct professor here at Penn. Um, So today he's going to be talking about some of his work on machine programming that he's been doing at Intel for the last few years. So yeah, please join me in welcoming him, and I'll hand it over to you, Justin.
Great. Thanks, Osbert. So first off, thanks for inviting me. I'm really excited about the Neurosymbolic Center that you folks have recently stood up. And uh, as a member of the advisory board, I'm really excited to see where you take it. And also thanks to all of you who've attended today. And feel free to interrupt me with questions at any point. I actually prefer more interactive talks than monologues. So if you see something that just have a burning question, just dive right in. So as Osbert was mentioning, I'm a principal scientist and I'm the director and founder of the Machine Programming Research Group. Oh, I've been working on machine programming since about 2016, and I'll give you a more precise definition of how I see machine programming shortly. And then I also have been working with Penn for several years as well, and I'm an adjunct faculty there uh, with Osbert and others. Okay, let's see if I can change slides. There we go. Okay, so before I dive into technical things, I'd like to give a little background on machine programming research at Intel. The first is I'd like to just mention that it's a pioneering research initiative at Intel, and what this means is we are investigating machine programming for the long haul. This is not something that we are going to invest lightly in. And to be a pioneering research initiative at Intel, you have to go through several checkpoints where you have to have buy-in from several executive leaders across the company before they sort of flip the switch and allow you to be considered pioneering. And we achieved this about summer of 2019. And since then, we've launched the group and we're continuing to grow. At this point, we have hundreds of people across Intel doing both research and engineering for machine programming. As far as MPR's goals, we really are focusing on two fundamental charters. What we are trying to do is reduce the time that it takes to develop all aspects of software. And the goal, our long-term goal, is to improve our productivity, or essentially reduce the temporal duration of software development by 1000x. And I realize this sounds a bit audacious, but if you look at some of the emerging research in constrained spaces, we've already achieved 1000x improvement. So for example, the halide autoscheduler work out of MIT with Jonathan Reagan Kelly, I think it's joint with Berkeley as well. They've already achieved something like 1800x improvement in optimizations that it would take over a normal expert programmer. So we do think that this is achievable. It's easy to get these types of results in constrained spaces. It's much more challenging to get these types of results more generally. The second charter is around quality. And by quality, we really are referring to all characteristics in which one might evaluate software. And those can be things like correctness, performance, maintainability, security, and so forth. Modularity. So the quality is meant to be a bit nuanced, and that it can be shifted and perturbed to whatever the end user cares about. So for example, if you're working in a real-time system, you probably have very hard real-time constraints that need to be met. Whereas if you're working in a system that is sort of a mobile, lightweight, low power device, your constraints might be different, and the quality characteristics would then differ for those environments. So the long-term charter with MPR in the automation of software and hardware is really around these two different principles. And I also want to mention that in machine programming, we consider this to be the automation of software, but also hardware. And this is principally because the development of hardware oftentimes is through software. So if we can automate these pieces of software, the byproduct will likely be the automation of hardware as well. For machine programming at Intel, we principally follow these three pillars. So in 2018, we jointly published with a team of really outstanding professors at MIT this paper. And this is the driving force across not only Intel Labs, but really it's starting to become across the entire company. In fact, if you were to visit my webpage, you may notice that I have a little picture of the three pillars of machine programming. I actually stole that from Bob Swan, our CEO, when he was presenting this topic to his executives. So we are really sort of broadcasting these three pillars across the entire company in the endeavor to get this type of acceptance and this type of mental model adopted for all the engineering groups, not just Intel Labs. And very briefly, what these three pillars are is intention, invention, and adaptation. Intention is principally about trying to understand the ideas that the programmer or non-programmer is trying to express. Traditionally, these ideas have been expressed using code. But as we move forward with machine programming, we anticipate that there will be many other ways that humans, programmers or non-programmers, may then present their ideas. Some of them may be through natural language, some may be through visual diagrams, it might be gestures, things of that nature. In addition to building systems that can understand the intention of the programmers and non-programmers, we also want to be able to lift the semantic meaning from existing code. So in the intention pillar, we're also concerned with looking at legacy systems and trying to infer out what those systems are intending to do, so then we can adapt those systems and reuse that software in various ways. So once the intent is understood from the user, we then shift to the invention pillar. The invention pillar is principally concerned with the discovery of new algorithms and data structures to fulfill the intention of the user. Usually what we've seen with the early work in invention is it's not really inventing something in terms of it's constructing something novel. In fact, what it tends to do is just take existing components and perhaps combine them in ways that are novel. There are, though, some cases, there's a few different emerging pieces of research that I've seen where the inventive systems are actually discovering something novel. That is something that humans hadn't already constructed previously. And just from my personal perspective, when I think about the three pillars, the pillar that gets me the most excited is the invention pillar. And part of the reason for that is I feel that invention hasn't been explored as deeply as the other three pillars. Another part is I think that building inventive systems tend to be a lot more challenging. And then lastly, if we think about science advancing as a field, I think that historically, most of the discoveries that we've made, maybe all of the discoveries, have been by humans. I think that it's a really fascinating idea to consider that we may have discoveries made by machines. And so this is something that really kind of keeps me awake at night, trying to come up with these new inventive systems. So once we have the invented system, that some sort of higher level representation, what we then tend to do is move to the third pillar, which is the adaptation. For adaptation, what we want to do then is take the higher order representation and then lower it to the specific hardware and software ecosystem that is what the user wants to run this system on. And this is important because if we try to go essentially directly from intention to adaptation, we are building a sort of brittle system in the sense that it's specialized to one particular environment, where oftentimes what we find is when we're constructing these systems, if that system, if that software system is valuable, it could be reused and repurposed in many different systems. So it's almost like you have the inventive system in place, and then once it's in place, then you can augment it into all these different channels, where then that system can be useful across your laptop, your mobile device, supercomputer, data center, you name it. And one example of this might be, something like Zoom, right? That we're using Zoom. I'm using it on my laptop, but some people may be using it on their phone, and some people might be using it on a desktop. And these different environments may require different adaptive principles to be effective. Okay, so now we sort of understand the driving force behind machine programming at Intel with these three pillars. One thing I'd like to just quickly talk about is, when I think of machine programming, I think some of you may have seen this slide. I tend to think about it in terms of two different areas. And by no means do I think that this is precisely correct. This is just the way that I think about it, is that I tend to think that there's a stochastic side and a deterministic side. And in the stochastic side, it tends to be the space where we have machine learning systems or other sort of approximate statistical models that aren't necessarily deterministic, in the sense that they can be 100% reproduced every single time. There's some stochasticism present, but these systems can be very useful, as we've seen with deep learning and using things like neural programming. There's a lot of headway that we can make with stochastic systems. On the other hand, I think it's important to not be blind to deterministic systems. These are systems that I think are more in the formal space. And these formal systems have been around for quite some time. These are things like using SAT solvers or SMT solvers that you're trying to mathematically prove some characteristic of this piece of software. And then once it's fulfilled, you know that the piece of software is correct. Historically, we've seen, or at least it's my belief that we've seen, that some of these deterministic systems can be limited in the size of the program that we're trying to synthesize. But when we fuse deterministic systems with stochastic systems, oftentimes we see this really interesting interplay where the stochasticity can help the deterministic system be more effective because it can do probabilistic type of search and things of that nature. The other thing that I think is kind of interesting about this is a diagram that I generally present when I'm explaining machine programming. But in the context of neurosymbolic research, I think that there's a very clear path here on how this breaks down. This is based off of the initial kickoff meeting that happened a few weeks ago, when I was asking Armando and others how they precisely defined neurosymbolic. And my understanding is the neuro part is really about the exploration of sort of these neural representations of a system. And that could be with a neural network. It could be something else that perhaps is also differentiable. It's not entirely clear, but at least the neural network part is one piece of it. And then on the other hand, the symbolic part, I think, fulfills the sort of formal method side. So it's interesting to me that even though the neurosymbolic folks are sort of working in a separate space, there is overlap between what they're doing and what machine programming is doing. And I think also the way that we are thinking about the future of these systems. So hopefully that makes sense. And if it doesn't, feel free to chime in and ask any questions.
So I have just a quick question about this picture. I guess there's a distinction between the technique for generating a program and the program itself, right? So you can talk about stochastic versus deterministic synthesizers, and you can talk about synthesizing stochastic and deterministic programs. So I'm wondering, like, in this picture, which side of it you have in mind, or what your thoughts are about.
Oh, so I generally am thinking about this being, yeah, so this is a great question. I think that I'm thinking about it in terms of the way that we're synthesizing the program, and not necessarily the mechanisms that one might employ as the form of synthesis. So for example, I might think that, and it could be both, right? As you pointed out, Osbert. So I can imagine that I might use a neural network to help me understand how to build a program that then would spit out the instructions that then I would use to then fulfill whatever specification or input-output examples I have, something of that nature. And then the output would actually be the instructions. It wouldn't be a neural network. I would use the neural network as sort of the guiding force to then, the sort of the backbone to help me synthesize it. On the other hand, you could also do what you're describing as well, the second piece, where you could actually train a neural network that actually acts as a replacement directly of the code, and that becomes the actual thing that becomes synthesized. So I tend to think about it in this particular space of more the techniques that we're using to get us to the synthesized program, and then what we actually generate as that program could be a variety of things.
Okay.
Does that answer your question, Osbert?
Yeah, I think so. Thank you.
Okay, yeah, great question. So now that we have some background, I plan to spend the rest of the talk really just talking mostly about debugging and a little bit on these three different systems that we've built over the last couple of years. There is one system here that most of you have probably not heard of, even if you've heard me speak before, and that's Control Flag. And Control Flag is a system we just recently built, and I'm pretty excited to share some of the things that we've done with it. So let's dive into these three systems, but before we do, let's get a little bit of a background on debugging. I suspect that everyone on this call is aware of debugging, but just as a refresher, really what we're trying to do as we develop software is ensure that these quality characteristics are at some bar, that as software evolves, software has a tendency to degrade the quality of these various characteristics in different ways. For example, we may be changing the code and the performance reduces, or we add a new feature and suddenly we break correctness. So what we want to do through the development is ensure that these quality characteristics remain at some bar. And when they go below that threshold, we tend to refer those as bugs. And sort of the severity of the bug, I think, depends on what tends to be most important for that different piece of software. But the process of observing, root causing, and mitigating these bugs is generally known as debugging. Before we go further, I think an important question to ask is, well, how expensive is debugging really? Because if debugging isn't that expensive, maybe we should spend our time in machine programming doing other things. But if we look at a study that was done by University of Cambridge in 2017, and this was done for data that they had in 2012, we can quickly see that the global cost of debugging is about $625 billion across the globe. And not only that, 50%, approximately 50% of all the development is actually debugging. So if we were able to improve the debugging in such a way that it no longer exists, if we were able to somehow get intentionality perfectly correct, the higher order idea is that we may not have bugs anymore. That it's my belief that when we have bugs, it tends to be a violation of intention. So the higher order idea here is that if we're successful with machine programming, we could potentially eliminate the entire space of debugging. And by doing that, we could effectively improve the productivity of all our developers by 2x. And again, this is a super audacious goal. I don't think this is something we're going to achieve tomorrow, but I think this is something we should be striving for.
May I ask a quick question? Hi, this is Yisong.
Yeah.
And I'm sure you know this better than I do. Like, sometimes the intention is implemented correctly, but the intention was buggy, if you will. So I was wondering maybe you can just briefly speak on that.
Yeah, Yusong, that's a great point. And one of the ideas that we have when we look back at the pillars, and I didn't talk about this today, but I talk about this in other talks, is there tends to be sort of this interplay between intention and invention, that we sometimes will talk about these systems as conversational programming, that as the programmer is specifying the intention, like you pointed out, there may be under specification, over specification, or things that are just simply incorrect. And I think that we need the emergence of these systems that have the ability to interpret that intention and try to understand if that intention is correct. So for example, one of the sort of quick machine programming examples I tend to use is I might talk to my phone and say, computer, notify me whenever I'm near a Starbucks. And then if I have a really excellent conversational programming system, what it may do then is take that phrase, notify me whenever I'm near a Starbucks, and then say, okay, so I don't know what notify means. I need to figure that out. I don't know necessarily what near means. Near might change based on the different type of mode of transportation that this person is using. And then Starbucks, I have a sort of a symbolic understanding of what this means, but they may be over specifying that, and maybe what they really mean is coffee. And then there's also things that are absent, right? That it could be that the person is trying to get to the Starbucks when it's open because they want to get coffee. And so the machine would then have to infer these things that are actually completely absent. So I think you're absolutely right that what we will likely need are these conversational systems that, and we'll see one example of that with MISM shortly, that will then sort of fact check the user to understand in a very sort of deeply semantic way whether or not the intention the user is expressing is actually correct. I think it's a fantastic area of research, and there's some emerging work in this space, but it's actually pretty immature from what I've seen. Does that answer your question, Yusel?
Yes, thank you.
Okay, yeah, thank you. That was a great question. So going back to debugging, we tend to see that, yeah, 50% of software development is debugging, and so this seems pretty expensive. That's a lot of money to be spending every year. And keep in mind, this data is from 2012. With inflation, I suspect it's grown quite a bit. So with that in mind, we'll talk a little bit about some of the debugging systems that we've built. The first is AutoPerf, which we presented at NeurIPS last year. And very briefly, AutoPerf is a performance regression system, and it uses these 3 different pieces of technology. If you don't know exactly what zero positive learning autoencoders and hardware telemetry are, no worries, we'll talk about that in just a second. But before we do, maybe we can see some sort of motivating example. And this one is pretty interesting to me because it's a real system, and the type of performance regression that was introduced is, in my mind, not so obvious. So what you see on the left is a MySQL 5.5. And what they have is essentially this mutual exclusion lock that will only allow one thread to access a piece of memory. And they're doing this because they want to ensure that as that piece of memory is changed or read, they don't get a violation of correctness, that it tells them essentially the right value. But anyone that's written parallel code or taken like a parallel programming class can probably look at this code and say, well, gee, this is kind of naive. This is going to be really slow. And so the MySQL folks realized this, and then they upgraded to MySQL 5.6, where they then created an array of locks. And then the array essentially is a location for each of the individual threads, and each memory is given to a particular thread. And then when they need the summation of all the values, they just lock all the locks, they add all the values together, and they get the total sum. From someone who did his PhD in parallel computing, I can say that there's nothing obviously wrong in this code, at least to me. But when you look a little bit deeper, when you look at the microarchitecture that this will run on, specifically in the cache lines, what you see is that this actually can introduce false sharing. And the false sharing you get, because there are so many threads that can contend on this cache line, you actually end up decreasing performance more than the original code by 67%. What's interesting though is the MySQL folks did all of the normal rigorous testing with their performance regression systems. It's just that the performance regression systems that they had didn't give them the capability to detect this performance bug. And that's because the traditional systems tend to introduce what's known as the probe effect or the Heisenberg effect. Whereas if you start to probe, you change the signature of the program, and therefore the performance bug sort of elides away. So with this motivation, this is why we built AutoPerf, is we thought this is a good area for machine programming. And what's nice about this, going back to Yusong's point, is when we're trying to build performance regression systems, we tend to know what the intention is. The intention is simply don't degrade performance. It's just basically known. And since that intention is known, it's pretty straightforward to build a system that is going to try to fulfill that intention. And that's basically what AutoPerf does, is it essentially tries to invent the performance regression test that's needed for any particular piece of software, and then it adapts that test to different hardware architectures or different software environments. And it does this using these 3 different techniques: zero positive learning, autoencoders, and hardware telemetry. ZPL, zero positive learning, is essentially the type of learning where you learn principally on nominal data, or what's known as the negative space, if you're talking about anomaly detection. This tends to be important for performance regression bugs because it basically is saying you don't have a performance bug yet, but you may. And we need this as a baseline to essentially give us a point of stability, or at least AutoPerf requires this. The next piece is it uses autoencoders. Autoencoders are a specific type of neural network that act as the identity function of a particular input. And the autoencoders essentially are trying to behave as a threshold gauge, that they tell us if the threshold is exceeded or minimized to some value. And if it goes in either of those directions, then it sort of throws a flag. And in those cases, we know that there's some sort of performance anomaly. If the performance anomaly is an improvement, we simply just ignore that. We can look at wall clock time. And if the performance is a degradation, then we do deeper analysis. And then the last piece is that we use hardware telemetry as the measurement for the software. And this part we think is critical, because what we've seen historically is when you try to measure the software performance in a more software-oriented fashion, you can tend to have that Heisenberg effect. From our initial results, we hadn't seen any false negatives. This is not to say that they can't emerge. It's just in our experiments, we didn't see that. And then here's just a high-level system diagram in case you're curious. Just real briefly, the snapshot of the results is shown here. And what you kind of want to see in this graph, this true positive versus false positive rate, is you want to see an inverted L. And we don't quite get that because we do have some false positives that you can see at the sort of the 1.0 y-axis, 0.1, 0.05 something axis. And that's sort of the trade-off that you tend to make with complex anomaly detection systems. Is it's usually very challenging to have both no false negatives and no false positives. You tend to have to make some kind of choice. And because we don't want false negatives, we don't want a performance bug to be missed by AutoPerf, we tend to have a bias toward false positives. So that's actually an intentional sort of design decision on the threshold metric.
Wait, so just to kind of clarify a little bit what's going on in the previous slide. So that what is the autoencoder like trained on to take?
Yeah, great question, Albert. Sorry, I think I just glossed over this. So what we do is we essentially take sample data points of the program executing captured in the hardware telemetry. So in particular, we use Intel hardware performance counters, which give us essentially a rough approximation of the performance overhead for some duration of time. And then that data is used as input into the autoencoder. If it can track that data in such a way that it can reproduce sort of a rough approximation of it, given like a function signature, then we know, generally speaking, that we haven't introduced a performance anomaly. So for example, you might have function 1, we'll just call it, function version 1. And the autoencoder will take that and then a whole bunch of hardware telemetry as input. And then we'll train it such that it can reproduce those values. Then we'll take function version 2. And then we will also capture the hardware telemetry values. We'll then output it in the inferencing phase. If it can't reproduce those values, we have a speculation then that we've introduced some sort of performance anomaly. Does that make sense, Osbert?
I see. So this is trained across different executions of the same function, I guess.
That's right. That's right. Yep.
And I guess the other question I had was, so you said, I guess one of the key challenges was that telemetry affects the execution of the program. So is the key idea for getting around that using the hardware performance counters, or was there something else involved?
No, that's exactly it. Yeah, is that what we find is what most people may not know is almost all modern CPUs and potentially other types of compute architectures have these hardware telemetry events that are running always. They're always on in the background. And so right now on my laptop, I have these hardware performance counters that are actually executing right now. And what we find is they tend to introduce very minimal overhead, which is why they can stay on all the time. And because of that negligible overhead, we tend to find this, so this is important to qualify our claims here. For like a real-time system, this negligible 4% might not be negligible. But for the cases that we looked at, it seemed to not perturb the performance such that we then couldn't detect the performance bugs. Does that make sense?
Yeah, got it. Thanks.
Okay. Yeah, these are great questions. So now we'll go into MISM. And MISM is a semantic code similarity system that has sort of two novelties. One is the structural representation, and the second is this learned neural scoring algorithm. MISM is short for machine inferred code similarity. And this goes back to Yushang's point about understanding intention and how one might be able to infer things that might be wrong about a user's intended intention versus what is actually expressed. And hopefully this will make a little bit more sense as we talk about this. The core idea behind this system that we built is, as we start to move forward in developing software with machine programming systems, we might want to build something like a code recommendation system. This might be an expert virtual assistant that as you're writing code, the system is sort of saying, hey, I can complete this line for you. I think that Microsoft's IntelliSense already has this. There's a startup called Kite. I think there's Tab 9 that is also doing something like this. And that's super cool. That's great. So we're seeing these early emergence of these systems. But we think we can go further than just a single line of code. What we would like to be able to do is perhaps complete an entire algorithm that a user starts writing pieces. And one might actually think of Armando's sketching system as one example, is that instead of Sketch filling in the holes, imagine if just the holes were in place and the system then fills out all the other details. Like, these are sort of the grand hopes that we want to achieve with these recommendation systems. The other thing is, when we are building these recommendation systems, it tends to be that they need to understand code similarity. If that's the case, then they may be able to infer certain things that could be wrong about the current code, going back to this point about a misrepresentation of intention. And so the code may have what looks like a correctly specified intention to the user, but the system, through its understanding of the semantics of the code, may realize, oh, that's actually wrong, and I'm going to recommend an automated bug fix to them. So with all of this in mind, when we build these code recommendation systems, it's our belief that you tend to need code similarity. And code similarity is this open research problem, and it's basically the idea that there's a few different ways to do code similarity. We're interested in semantic code similarity, which is the space where we can take two or more code snippets, and then even if those code snippets are syntactically divergent, if they are semantically convergent, we will then flag them as similar. And this is something that is not super easy. It hasn't been really explored too much. There's been a lot of research in compilers over the last 70 years where we've done things like syntactic similarity analysis, and we can do great things on optimizing loops and so on and so forth. but trying to infer the semantic meaning of code and then be able to produce potentially an entirely divergent code snippet that might execute more efficiently on different architecture or different ecosystem. This is, in my mind, a much more challenging problem, and the problem that we're starting to try to tackle with MISM. And so you can see a little bit of the details behind that here. What we're really trying to understand is, what is the software actually doing? We don't care as much about how that piece of software is doing it, that we want to understand all the different possible ways that a piece of software can do a particular thing, but how it does it is less important in terms of semantic code similarity than what it is actually doing. And we believe that this is sort of fundamental to many MP problems. Once we get really accurate code similarity systems, especially semantic ones, then I think that we can springboard the field forward. So one example is, you may have pieces of code that are semantically similar and syntactically dissimilar. If you have a semantic code similarity system, you tend to be able to identify these things. You could also have code that is semantically similar and syntactically similar. Well, we can already sort of do that one, right? That's just basically looking at pieces of code that compilers have been for a long time. And then, of course, there's the two other areas where they are syntactically divergent and semantically divergent, and then semantically divergent, but syntactically convergent. And that last space, I'm not sure how many problems exist, but it would be interesting to see if someone did some research in that space to find if there are any actual cases there. So anyway, not to get off on a tangent, to show you just a high-level overview of what the architecture looks like for MISM, you can see it here. And I don't expect anyone to be able to grok this diagram. Instead, I just want to sort of highlight the novelties of this. The first, in my mind, is the CAS structure. CAS stands for Context-Aware Semantic Structure. And the idea behind CAS is that many of the structural representations we've had in the past are sort of have a high level of syntactic bias. And what we've seen is, when those representations have a bias for syntax, they could easily misrepresent the intention behind that syntax. So with CAS, we intentionally drop a lot of the syntax, and it can be configured in hundreds of different ways. But one of the most sort of abstracted out representations allows you to pretty much drop almost all the syntax, and you just sort of try to capture the structural representation. What we find is that when you couple this with advanced stochastic systems that then try to learn the similarity score, they can do pretty well. Whereas if you don't use a semantic representation, instead you use a syntactic representation, you tend to not get the same type of accuracy, especially when you have that case I was referring to before, where you have two pieces of code where one is of syntax A, the other is syntax B. These two syntaxes are not convergent at all, but the semantics behind them are highly convergent. If you tend to build a syntax-driven system, it tends to not be able to find those things that well. So that's the first novelty. The second novelty is just the way that we have this sort of open-ended back end for learning the similarity score. And the reason why we do this is what we have found is that it doesn't seem that there can be a universal similarity score that we can sort of use out of the box for all pieces of code. And this kind of makes sense, right? If you think that if I'm writing in a language that is object-oriented, it might pay attention to certain structural details that a language that is functional, like Haskell, won't have, and so on and so forth. So instead of having a fixed similarity score, we allow that score to, or that algorithm to be learned. And that's shown sort of here in the bottom. The way that MISM is designed is you can actually replace any of these components with something else. So this is just a higher order structural sort of architectural representation. If you wanted to, you could put in a different representation than CAS. You could use something other than Siamese deep neural network, and so on and so forth. And then just very quickly to see some performance data, we've compared MISM to 4 different state-of-the-art systems. The MISM performance is these blue bars. We've looked at over 350,000 full C and C++ programs with 400 unique classes. And in pretty much every case, what we've seen is that MISM will be at least as good as the other systems, and in many cases, it will perform better. Any questions on MISM before I continue to the last part? Okay, super. So the last system is control flag. And I'm super excited about this, mostly because I kind of figured out control flag one night when I was walking my dog. And, so I go on these walks with my dog and I kind of just lose myself in my music and my mind starts to wander about machine programming. And I was trying to figure out how we could get over some of the challenges we have with the lack of labels in these code repositories. That we have these massive code repositories, like GitHub has over 200 million repos, but almost none of it is labeled. And it was really bothering me because it feels like there's so much untapped potential in those repos that if we could just figure out how to use that data meaningfully, we could start building more advanced systems. And that led to the discovery of the control flag system. So let's talk a little bit about what all these words mean, idiosyncratic and control structures. So what you see in front of you, if you're familiar with the C or C++ programming language, are 2 code snippets. The first one is doing an assignment of the value 7 to x inside of an if statement. And then if that is true, which it always will be, then y will be set equal to x. The second code snippet is doing a conditional evaluation on equivalence to see if x is equal to 7. And if x is equal to 7, then y will be set equal to x. Now, what's interesting about this is, in my mind, one of the things that's interesting is both of these code snippets are legal syntax in C and C++. The challenge we have now is if one were to see this first code snippet, I think that those of us that program in C and C++, we may quickly sort of infer that, well, I'm not sure the programmer meant that. What I think they probably meant is the second one. But what's interesting is that assumption, I think, is based on a bias to the environment that we're in. So for example, there are some programmers that actually really use this first one as sort of the side effect. Now, this is sort of a bizarre case. I don't know that I would use it this way, but doing assignment inside of ifs is sometimes seen as sort of like a way to short circuit out the logic to make things a little bit more compressed. So the big takeaway here is it may be an error for this first code snippet, but it may not be. It may be intentional. And so what we do know is without comments, if we were just to see these arbitrarily, we don't actually know what the programmer's true intention is unless those are specified somewhere else. Again, going back to Yuzhong's excellent point about sort of a misrepresentation of intention. So what control flag tries to do is learn these idiosyncratic patterns for a repo. And then based on what it learns, it can then tell you whether or not it thinks that this is what you intended, or it can tell you if it's something that it thinks you didn't intend. And what's really exciting about control flag is the higher order system, the only part that humans have to be involved in is this first part, this step 1.0, is that we have this notion called semi-trust. And the idea of semi-trust is we don't know for sure if we can trust this code repository, but we have a belief that we can based on certain environmental factors. For example, it may be that this GitHub repo has hundreds of stars. It may be that it's forked a long time, many times. It could be that the code repository has been in existence for decades, or it has, billions of users. We can use these sort of environmental factors to help us infer semi-trust. It doesn't mean that necessarily we can trust all of the code that's in that repo, but rather it may give us an intuition of a belief of trust. So once that's done, the rest of the system actually just does its own thing. That we do tell it what the control structures are, but we don't tell it any rules. So we don't teach it about things like how to properly use if statements, what a for loop, how a for loop should be used, how it shouldn't be used. And what's fascinating is as we've sent this out to learn about the world, when it comes back and then we have it analyze other repos, some of the things it finds are spectacularly interesting. For example, we sent it out into the world and it learned, I don't know, from several dozens of millions of lines of code. And then we pointed it back at an Intel repo. And I think for confidentiality purposes, I can't tell you what repo it was, but we pointed it back at this repo and it came back and said, oh, I think that there's a problem here. And what it had found is that there was a misuse of pointers, that it was not doing error handling for the pointers correctly in this production quality code that we're using. What we were so fascinated about is we never taught it anything about pointers. So this is like incredible that it not only learned what pointers are, it actually learned the proper use of pointers all on its own. So this is pretty exciting for us. Just to summarize, control flag doesn't have any embedded rules about these anomalies. It's mostly self-supervised, except for that first piece about semi-trust, and that we just recently breached the 1 billion line of code mark. So we're not sure, but we think this is the first or one of the first systems that is a machine programming system that's learned from over 1 billion lines of code. And the more data we give it, the more it seems to improve in the things that it can observe. We'll be presenting control flag at NeurIPS in just a couple weeks at the ML for Systems workshop, if you're interested to learn more about it. And I can also mention that we have sent it to curl, so the open source upload and download software system that's been around for, I think, almost 20 years. And we had it try to just observe the curl source code. And it found something really interesting. We then took that data back to the curl team, and the curl team acknowledged that this is this weird anomaly, that it's non-maintainable code, it's misrepresenting what the intention is. And so the curl team then created their own pretty big structural change, and then integrated that structural change and now has patched that bug. So we've seen cases now, both internally at Intel, where control flag can find some really interesting things, and then also externally in production quality open source systems that have been hardened for decades, and control flag can still find some interesting cases that other developers had historically missed. So in conclusion, I just want to, as a reminder, machine programming research is pioneering at Intel, and we're really excited about this. I oversee the MP research group, and just as a reminder, we are hiring. So if you have a PhD or beyond, postdoc, this type of thing, and you're interested in this type of work, please let me know. I would love to talk with you. And even if you're not someone that I can hire into the team directly, if you're an academic that would be interested in collaborating, like many of the folks in the NSF expeditions, please reach out with ideas. I think as many as you know already, I really do love collaborating with others, and I'm always eager to work on new, interesting problems. So we looked at a few open problems today, but there's many more than just the 3 systems that we looked at. And these are mostly focused on debugging. I think that there's many other areas we can analyze outside of debugging, but debugging seems to me like a really good low-hanging fruit area that we can make strong forward progress. And what's exciting about working in the space of debugging is, from my perspective, I don't know of a single programmer who likes to debug. So I don't think we're going to have the fear that anyone's going to be upset that we're sort of helping them debug faster. At least this is my belief. So I think this is a really good space for us to dig in, and maybe if we all work together, we can eliminate that 50% and then perhaps jump to that 2x improve productivity. So with that, I think I'm done. I guess I can open up for questions or whatever you think is appropriate, Osbert.
Yeah, so thanks for the great talk. And yeah, I think we have some time for a few more questions if anyone. So I guess I have one just to get started. So I guess the last two systems you talked about, I guess the second one was you were kind of emphasizing that the semantics, you really care about the semantics of the code. But then it seems like in the third one, you're actually kind of purely looking at the syntax. So I was wondering, and I feel like there was this transition in NLP as well, where for a long time people were thinking about semantics, but recently, like now it's just throw all the text, billions of words at a
right.
Works, right? So what are your thoughts on kind of that tension? Do you think that including something about semantics is still useful in programming for programs, or is it maybe just more models on source code, larger models?
Yeah, so first of all, I think this is a fascinating question. And in discussions I've had with others, I definitely go back and forth on this. Sometimes I really hate how much attention to syntax we pay, because I think that this can hide some of our ability to infer semantic meaning, which I think is fundamental for many problems. On the other hand, you made a really great point, right? That I didn't even mention this, but control flag is principally syntax driven. So it's just learning from the syntax, and yet it's found some really interesting things. So could we do something that maybe uses both? Actually, that's our plan. So one of the things we want to look at next with control flag is, rather than building, these ASTs that then are going to do interesting things, what if we built ASTs coupled with the CAS, the context-aware semantic structure? Could it then observe even more interesting things, rather than just these sort of one line of code isn't exactly right? Could we then pivot it to, oh, this entire function here seems to be slightly off of what we think it should be? And we have another example over here of something that maybe Missam had learned that says, yeah, this is what we think it should be. So I think that there's a lot of potential in combining these two different things, where you have something that is syntax heavy and you have something that is semantics heavy. And then if you merge them together, I think that there could be new things that either system might not be able to find on its own.
Right.
So yeah, that's a fantastic question.
Okay, yeah, that makes sense. Thanks. Yeah, any other questions? Anyone else have a?
One question that I actually have, Osbert, is I'd like to invert that question and ask you that same question, because I know in the past you and I have spoken about this, and we are both working in this space. Do you have an opinion on this? Are you of the belief that we could take these two things and combine them, or do you think it's principally going to be syntax or semantics, one or the other?
Yeah, I mean, I'm not sure right now. I think it's still very much an open question. I mean, I definitely think it's different from natural language. So I brought up that analogy.
Right.
Like in NLP, the semantics is really a much more amorphous, whereas programs have much more clear semantics. But I think even so, I guess right now, with the success in NLP with GPT-3 and everything, it does seem like maybe all we need is syntax. But who knows? I think it remains to be seen. Oh, sorry. Go ahead.
Oh, I was just going to say, I think one of the things that you do get with code is the ability to run it, which is something that you just don't get with natural language. So that gives you this very clean, very precise connection to the semantics, right? The ability to just run it and see what happens and incorporate dynamic information. And also just the fact that we have this big toolkit of program analysis techniques that can tell us true, correct things about the code that can potentially be beneficial, can supplement the information that you can get directly from the syntax.
Right. Yeah. So Armando, I think that's a great point. And one of the things that I like to sort of remind folks about is we historically have paid a lot of attention to the code as sort of this superficial layer, that represents the software. But as you point out, that there's actually many different layers that we could be looking at. We could look at intermediate representations, we could look at dynamic executions, we could look at the hardware telemetry data that's produced from that dynamic execution. And so there's like this, there's the layers and dimensions of depth that we may not get from NLP that I think could give us deeper insight into sort of these semantic understandings. So yeah, this is great. Just one quick comment about GPT-3. I can't control myself. So I've been reading that it's been able to produce some lightweight code, but there's also a lot of pushback on some of the things that it's been generating, in that it seems that many of the things it's generating make coherent sense, but some of the things I've read is that it doesn't truly understand what it's generating. So then the actual semantics of these sentences that it's producing, these paragraphs, while they are cohesive, it doesn't actually have the ability to infer out the meaning of those things. That's I think a big disconnect that we need to resolve. And again, maybe something like GPT-3 could be used for source code in all these dimensions and then infer out those layers of semantic meaning. But currently, in its current state, I think that's a big gap that might inhibit us from being able to do things like massive code morphing, lifting from one system to another, working on heterogeneous hardware, that type of thing.
Yeah, I think that's a good point. But I guess the question is whether pushing, just building bigger models will get us there, or whether there's some.
Right.
It's not clear to me, yeah, I think maybe we have time for one or two more questions if anyone else has.
Yeah, I have a question if no one else. I mean, I don't want to ask all the questions, but so these methods look promising, and I'm wondering, when do you think you'll be able to actually rigorously verify how much they've reduced cost of debugging? I understand that these are sort of very isolated or targeted projects, but at some point, certainly, we do this when we write big grant proposals. Certainly, I think Intel would ask for like a review, right? And a review, how far have we come? When might we start to see a transition towards massive cost reductions in debugging? How do you think about evaluating these things?
Yeah, so first of all, another really fantastic question that we've thought in good detail about. I think that so first of all, I don't know necessarily that I have the answer on how to measure this, because I think there's many sort of nuanced, intangible ways to consider this. Like, for example, if the code that it's generating is highly maintainable, then that might be a really good thing. And you may not see a savings initially, but in the future, you might get a huge savings. Like, this is one of the issues that I had with verified lifting, and that I've been sort of pressing Alvin Chung and others to try to address, is that the lifted code, when it's lowered to the new system, to ensure that it has good nomenclature, that we don't just drop it in and variable names have V1, V2, that then if that code needs to be maintained, maybe no one knows what the heck's going on. So with that aside, I think there are some ways that we can measure this. And one of the ways is, I think that we at Intel, we do have historic data on how long it takes a programmer to fix a bug once the bug has been identified. So one of the things we've been doing is helping them debug their systems, that they are able to do a couple different things. One, we are trying to identify the bugs for them proactively with these MP systems. And that one's a bit tougher because historically, I think when the bugs are observed, they tend to be observed when something breaks, either in a test case or in some actual deployed environment. With the MP systems that we're building, we're trying to essentially observe these bugs and hopefully observe them without customers necessarily observing them. So the window of time between when we observe it versus when it would have been observed is not entirely clear, but I think we can still use historical metrics as a data point. For example, we could potentially use the check-in time when the bug was introduced to the time at which it was found with these sort of manual or natural exploitation versus the time that it was checked in and then an MP system found it. So we could potentially use that point of sort of temporal analysis to tell us what the savings might be temporally. Another way is we're building a system that is, we call it PDD, the predictive defect detection. And what PDD does is, I think kind of interesting, is it looks at code that may be tending toward introducing a bug. And we are saying basically that a bug doesn't exist yet. But based on historical analysis of the code, what we've seen is that if you tend in this direction, you essentially have momentum moving this way with the source code, more likely than not, you are going to introduce this bug. So we are going to curb you off and stop you and take a more proactive approach. So then in that frame, what I think is super interesting, Yuzhong, is that it's almost like you reach an infinite improvement in time where the bug gets introduced and the time that it's fixed. The bug actually never even surfaces. So again, I don't necessarily know how to measure that. I mean, maybe you take the whole temporal time of when the programmer started to move in that direction up until the bug was fixed versus the new system, the PDD system, which is it takes the same example and then the amount of time for PDD to realize, no, you're moving in the wrong direction, and then the programmer fixes it. So that might be like another way. But I'd be curious to hear any thoughts that you might have, both online or offline, because I don't know. I think that this is sort of an open question. There's many different ways, I think, to think about it. And I would love to hear this.
At least in terms of an analysis, certainly that what you're saying reminds me of what people have done in econometrics, where they try to find ways of inferring basically what's a censored measurement or a censored variable, if you're familiar with that term. So there might be some insights from that line of work that could be useful. Like, when you deploy your system for the first time, naturally there'll be cases where some bugs are caught and some are not, just due to just the fact that your system is can't do everything at the first time, and whether you can actually use that natural variation to tease out these things.
Yeah, that's great. Another area that I'm also super interested in the same space is helping us get more exhaustive tests written automatically, and being able to generate sound tests. I think mathematically sound tests is not super challenging, but being able to do both mathematically soundness and completeness, I think, is perhaps untenable in some software systems. But I think that we can still make forward progress. And if we were to do that, I think that could also help quite a bit. And like you're saying, with this teasing out these bugs, that might save us a huge amount of time. And the savings that might come with it. Whereas if we didn't have these more exhaustive automated systems, we might miss them. I will say, though, that one of the biggest reasons why Intel is deciding for this to be pioneering is that we have already seen strides where some of the things we found have the potential to save Intel on the order of tens of millions of dollars with very simple, like a single observation of something, that just fixing it proactively before something terrible happens is this enormous win. And these types of things, I think, are a driving force as we move forward. One of my roles is actually to do these types of financial analyses and then present to the executives and say, well, here's how much MP saved the company this quarter. And once we get into the billions, I think machine programming is going to take over the whole company.
Sure. Makes sense.
Yeah.
Okay. Yeah, I think we're already past time. So thanks so much, Justin, for the talk, and thanks everyone for coming. So I think this is going to be the last webinar of this year. So hope all of you have a great break, and I'll see everyone next year. Thanks. Bye.
Super.
Thanks, Osbert.
Thanks. Bye.
Yeah, thanks everybody for having me. Appreciate it.
Bye.
Thanks for the talk.
Okay, super. Thanks. Okay, bye-bye.
Bye.